Welcome to our explainer. So, think about this for a second. We know more about the surface of Mars than we do about the deepest parts of our own oceans. It's kind of wild, right? We're about to take a dive into that unknown, a place that makes up more than 90% of the living space on Earth. We're talking about a world of bone-crushing pressure, absolute eternal darkness, and creatures so bizarre they look like they were dreamed up for a sci-fi movie. We're going to the deep sea.
And that's the big question, isn't it? What is actually down there? Below the familiar sunlit surface, there's this enormous hidden world that operates by a totally different playbook. No sun, no seasons. The rules are just different. It's a place we're only now, just now, starting to get a glimpse of. And once you know it, it's already facing a challenge that could change it forever.
So, here's our game plan for this journey to the bottom. First, we'll explore this truly alien world and the incredible life that calls it home. Then, we're going to look at the new gold rush, the industrial push to mine its resources. And that, as you'll see, is going to lead us to some really tough questions about what happens next to our planet's last real frontier.
All right, let's start the descent. As we go down, you have to imagine leaving everything familiar behind. Every single meter we drop takes us deeper into an environment that is more hostile and more strange than anything you'd find on land. Seriously, this isn't just a deeper part of the ocean. For all intents and purposes, it might as well be another planet.
This chart really shows you just how fast things change. Up top, you've got the sunlight zone, the epipelagic. It's where all the action is, photosynthesis, most of the fish we know. Then you hit the twilight zone, the mesopelagic, and the light starts to fade out. But once you pass 1,000 meters, boom, you're in the midnight and abyss zones. The light is gone, completely. The temperature drops to just above freezing, and the pressure becomes almost unimaginable.
And that pressure is really the biggest hurdle down there. To put it in perspective, the pressure increases by one whole atmosphere for every 10 meters you go down. At the bottom of the Mariana Trench, it's over 1,000 times the pressure we feel right now. It's like having 50 jumbo jets parked on your thumbnail. So how on earth does anything survive that? Well, it's because they're not fighting the pressure. The pressure inside their bodies is the same as the pressure outside. They've evolved these incredible specialized cells that stay fluid under conditions that would literally crush us into oblivion. Okay, so if there's no sunlight, there are no plants. So what does everything eat? The answer is something called marine snow, and it's exactly what it sounds like, a slow, constant shower of, well, leftovers from the world above. Dead plankton, fish poop, dust, all of it drifts down for weeks. Most of it gets eaten on the way, but that tiny, tiny fraction that makes it all the way to the bottom, that is the sole energy source for almost the entire deep sea ecosystem. It's this incredibly fragile lifeline. So if you're living in a world of total darkness, insane pressure, and barely any food, how do you make it work? The challenges are just so extreme that evolution got creative. This is where we see some of the most mind-bending adaptations in the entire animal kingdom. The strategies these creatures use to survive are unlike anything else on Earth. This comparison tells you pretty much everything you need to know. The number one rule of the deep sea is do not waste energy. Ever. Think of a tuna. It's pure muscle, built for speed. A deep-sea fish, it's the polar opposite. Its body is weak, watery, almost jelly-like, because building dense muscle costs way too much energy. Same for its skeleton. They're not built for a high-speed chase. They're built to wait, patiently, in the dark, with metabolisms so slow that some of these guys can live for more than 100 years. So what do you do when you live in absolute pitch-black darkness? Simple. You make your own light. More than half of all the species down there are bioluminescent. And this isn't just for looking cool. It's a high-tech survival kit. You've got the famous anglerfish with its glowing lure to attract dinner. You have others that flash secret codes to find a mate in that vast blackness. And my favorite, some creatures light up their own bellies to match the faint glow from above, making them invisible to predators looking up. It's called counter-illumination, and it's brilliant. There's this silent, dazzling light show happening down there all the time.
Now, that marine snow is like a steady drizzle of food, but every once in a while, the deep sea hits the jackpot. When a giant animal, like a whale, dies and its body sinks to the bottom, it creates something scientists call a whale fall. And it's not just a meal. It's a full-blown oasis in the middle of an underwater desert. And this is the really critical part to get. A single dead whale becomes a biological island. It's a massive injection of food into a world that is defined by starvation.
It creates this temporary hotspot of life that can last for decades, supporting generations of creatures that might live their entire lives right there on that one skeleton. The whole thing unfolds like a slow-motion play in 3 acts. First, the big scavengers show up, sharks, hagfish, and they strip the carcass clean in a few months. Then comes Act 2, the decomposers. This is where you get these bizarre creatures called oseducts worms that literally means bone-eating snot flower, and they burrow into the skeleton itself, digesting the fats inside. And finally, for decades after, the bones slowly release nutrients into the seafloor, feeding a whole new community. It's the ultimate recycling program. Absolutely nothing is wasted. For basically all of history, this incredible world has existed in total isolation. But that's changing, and it's changing fast. The same hunger for resources that has reshaped every corner of the land is now looking down, way down, to this new industrial frontier. And don't think this is some sci-fi future. This is happening right now. Just look at this timeline. For years, there was barely any interest. Then, around the early 2000s, it just explodes. Why? Because the metals we need for our technology, our phones, our batteries, our green energy, are getting harder and more expensive to mine on land. So companies and countries are looking to the ocean floor. The race to the bottom is on. So what are they actually looking for? Well, it's mainly 3 things. You've got these potato-sized polymetallic nodules just scattered across the vast flat plains of the abyss, and they're full of nickel and cobalt. Then you have massive sulfides that form around those crazy hydrothermal vents. They're loaded with copper and gold. And finally, you have cobalt-rich crusts that grow on the sides of underwater mountains. The key thing here is that each of these resources is found in a totally unique and incredibly fragile deep-sea habitat. Which brings us to the unavoidable question. We know what the prize is, but what's the real cost? What happens when you introduce heavy industry into the most sensitive and least understood ecosystem on the entire planet? The problem is, the impact isn't just in one place. It happens at every single step. On the seafloor, you have giant collector vehicles, think underwater bulldozers, scraping everything up, destroying the habitat, and crushing anything that can't get out of the way. Then, the system that lifts the minerals to the surface creates a ton of noise pollution, which could be devastating for whales and other animals that depend on sound. And it doesn't even stop there. The waste sediment gets pumped back out at the surface, and even the bright lights from the machines can totally mess with the light-based worlds of the deep-sea creatures. But you know, the most widespread threat might be the one that's hardest to see. Get this. For every 1 ton of those nodules they collect, they kick up as much as 5.5 tons of fine sediment from the seafloor. This creates these enormous underwater dust storms, sediment plumes, that can drift for miles. And for all the filter-feeding animals on the seabed, like sponges and corals that have been sitting there for hundreds of years, this is a death sentence. It clogs their feeding systems and literally smothers them. Now, here's what's really scary about the scale of this. Tests show that, yeah, most of that sediment cloud, like 98% of it, stays pretty close to the bottom. But that leftover 2 to 8%, that can get kicked up higher into the water column and get carried away by deep ocean currents for huge distances. What that means is the environmental footprint of one single mine could be hundreds, maybe even thousands of square kilometers larger than the area they actually mined. So that leads us to the final, and let's be honest, the trickiest part of this whole story. Where do we go from here? On the one hand, the demand for these metals is real. It's being driven by our need for green tech, for electric cars, for a sustainable future. But on the other hand, the potential for permanent, irreversible damage to an ecosystem we're just getting to know, that's also very, very real. This question says it all. How can we possibly write rules for a place we know so little about? Sure, there are international laws that say the deep seabed is the common heritage of mankind. It's a beautiful idea, right? That it belongs to all of us. But what does that actually mean when a giant machine is about to scrape it clean? To make good rules, you need good data. And that's the massive problem. We have a huge gap in what we know, a profound lack of baseline data. How can you possibly assess the environmental impact of a mine when you don't even have a complete list of the species that live there? When you have no idea how they're connected or how long it would take for them to recover? We're talking about creatures and ecosystems that operate on timescales of centuries or millennia. If you wipe them out, they may never come back. We are literally trying to write the rules for a game without knowing the players, the board, or even the stakes. And that's where we have to leave it. with the question that's going to define our relationship with the ocean for the next century. This hidden world holds both the resources we think we need for our future and biological wonders that are completely irreplaceable. We are standing right on the edge of a new industrial age in the deep, and we have to decide. Can we find a balance? Can we get what we need without destroying this final frontier? Or is the price of our progress going to be the silent, permanent loss of a world we never even got the chance to truly know?